everyone, welcome back to another video for the series. And today in this video I would like to share three very famous Olympiad geometry lemmas. And this video is actually the video that I'm making because in my previous video, while solving the 2001 USAMO problem 2, I mentioned that I will be proving and explaining few properties that I didn't prove it there, and this is the video that I'm making for it. So this is the one. And for the three very famous lemmas, we actually don't have the name and like formal proof of the lemmas, meaning I had to prove it myself, and there isn't like an official name and the written lemma itself. So we all know it, but we don't have like the formal description of it. So the reason why I'm saying this is because if you think my wording is wrong, or if you think my proof is not complete, please feel free to leave them in the comment below. My proof might not be original because these are quite famous lemmas and someone might have actually proved it, but I never saw a written proof of them. So I'm just going to share my personal insights on the proof that I wrote. So if you think I've any error or like incompleteness, please feel free to share them in the comment below. And three lemmas I'm going to share today are all intertwined together, and if we don't have the understanding of the first lemma, then we cannot understand the succeeding lemmas. So please watch the whole video and let's start. Our first one is let there be a triangle ABC if I will say just it's quite, I will just use maybe okay, sorry, I think I will just use I. If I sub 1 and I sub 2 are in circle of triangle ABC and X circle of triangle AB with respect to A, then I2 is the image of I sub 1 is the sorry, I'll say is the, because we don't know what image, right? Is the homothetic image of I sub 1 with the center A. I sub 2 is the homothetic image of, yeah, and homothetic and like spiral similarity, they usually come from projective geometry, but I don't think we really need like firm understanding of it. So I'm just going to draw a simple diagram to enhance the understanding and also proofs to help me prove the lemma. A, B, C. We have our in-center. Maybe I can just draw it. Something like this, maybe. Let me enlarge it. Oh, that's worse than what I thought. Oops. No, I just want to erase, yes. Oh, nice. Nice. I'm starting to see the shape. Yeah. Wait, I need to draw the X center too. Okay. Then make it smaller. Again. Nice. And let's draw our X center. So we are going to extend our line like this. Extend our line. Oh, extend our line. No. Why can't I draw a straight line? No way. Oh my goodness. Yes. Here is B and C. We actually need a good X circle here. Okay. This is not a pretty X circle, but I have no idea how to draw it. Oh, why does my circle look so fat? It doesn't look like a circle. And then can adjust them. Maybe something like this. This looks much more like a circle. Oops. Okay, one last time. We got this. Yay. So here and here. And what I mean by that is the ratio from here to here. No, from here to here. It's the same as here to here, here to here, oh, here to here. This one to this one, if they're all like collinear. So I'll just draw a linear line to demonstrate more on what I want to say. So let's draw a line like this. then this ratio to this ratio is the same as this ratio to this ratio, and it is also the same as this ratio to this ratio, and this is also the same as this ratio to this ratio. So I will just maybe I might just use visual proofs because I find them more elegant. So without lots of generality, let's just draw a red line like this, and we know that this is our angle bisector. So these two angles are the same. Moreover, this is 90 degrees. Like this. Then what we know here is this to this one is equal to this ratio to the long ratio. Maybe I might just move the red one a bit to yes. So let's look at the long ones. So we're going to use similar triangles here, and the similar triangle that we're going to use here is this one. Okay, so we know that this ratio to this length to this length is the same as this length to this length, and this length to this length is the same as you would have guessed, the blue one to the blue one to blue one, and that is because the blue length and these two I'll just draw them in green. Wait, actually, no, I will just use blue because they have the same length. Yeah, so let's say that this length right here is R, and this is a big R. Then we know that this length to this length is, so this to this is R to, so this is not like that mathematical, but for convenience, let's write it like this. Then we know that this length to the whole thing is R plus R all over R, which means this is equal to R plus R over R. So we know that the green ones this one and this one has the ratio of R plus R over the big R. So R over small r plus big R is the ratio of the short green one and the long green one. And that's quite obvious by using our similar triangles. Okay, then whoa, what am I saying? Oh my goodness. It is, sorry. The small r to big R. Why? Okay, so yeah, I'm so sorry. I was suddenly confused for some reason. So we know that the short green to long green is small r to big R. That's obvious using similar triangles. And that means this AR, I mean A I sub 1 to A I sub 2 is also R to big R. And because this segment here is R and here is R, these two triangles might be similar, like this small one to this big one. They might be similar, but they might not. And the reason why they might not be similar is because what if we have our blue like this? It is still R, so it's still R to R, R to R, but they're not similar to each other. But we know that this is not the case because let's divide our circles like this. Then we know that if you're going to look at the one that touches below this line, then we know that we're looking at the other one that is here. So we're not looking at this one. So same way, we know that this one and this one, they're not similar to each other, but this one and this one, they're similar to each other. So that's the basic idea that we're going to use here. So that's why we know that this length to this length has the ratio of small r to big R, and that's using similar triangles. And we can also go with the big ones to the big ones, and again using the similar triangle, we have small r to big R. So again, to encapsulate what I said, we could either have, because if we have R to big R, R to big R, and if we share an angle, the triangles might be similar to each other, but they might not be similar to each other because of one other case. But because we're specifically looking at the case where they must be similar to each other, we might look at the other case where they're not similar to each other, but we are purposely looking at the ones that they are similar to each other. Therefore, every point that if we define it this way, so define it a similar way using our red lines, then we know that they have the ratio of small r to big R, which means just choose any random point, and like here, that is on I sub 1, draw a line from A to that point and see where it leads to the big I sub 2. And if the point that we chose is above, I'll say like the half of the circle, then we're going to look at the intersection where it touches the upper arc of I sub 2. However, if you're looking at the lower arc, if we chose a point from lower arc of I sub 2, then we're also going to look at the lower arc of I sub 2. That way, we must have similar triangles. And because every case are the same, except for the tangent ones, but we already proved the tangent ones, we know that I sub 1 and I sub 2, they I will say quite map with each other. So I sub 2 is the homothetic image of I sub 1 with respect to A. That means we can recreate I sub 2 from I sub 1 by dilating with respect to A. Yes. So that's our first lemma. And their ratio must be R to big R. So now let's get into our second lemma. And the second lemma is the one that's actually, we also used our first lemma in our previous problem, but we also used the second one. So that is, let D be a point, or let D be the point, let ABC be a triangle where it's in circle, where it's in circle is tangent to side BC at point B. Define D, a point on segment on side BC such that BC define a point E on side BC such that BE equals CD. Then the X circle of triangle ABC from point A, from vertex A, or just from A, is tangent to side BC at point E. Let ABC be a triangle where its inner circle is tangent to side BC at point D. To define point E on side BC such that BE is equal to CD. Then the X circle of triangle ABC from point A is tangent to side BC at point E. I think that was a good description of what we have here. Oh no, let me do that again. I'm quite lazy to draw another diagram, so even though our diagram is not like that great, I'm just gonna use it. Okay, so we are saying that, let me enlarge it. We don't actually need the rest, so I think we can make our drawing a little more bigger. Yeah, something like this. And I want this part to be more clear. Like this. Then we define this point, we defined this point to be D. We define that point to be D. And our lemma here is to prove that this point right here is E. And these two are equal to each other. Let's just say that let I sub 2 meet B. Let I sub 2 meet BC at point F. Like, we don't know if it's E yet. we're just going to say they meet at F. Then what we know here is okay, so let's define a few other points. A, B, C, D, E, F, G. Never mind, let's use H instead. A, C, F, G, H. Yeah, H. So we know that E, F, A, B, C, D, I'm so sorry, F, G, H, I, point, I would say E prime instead. I think that would be better. Now notice that CD is equal to, let's just write information that we know, and that might be useful. We know that this is true. We also know that, whoa, my drawing is really bad, but E prime C is equal to Ci. Oh my goodness. Anyways, we also know that HB is equal to BE prime. Oh, and important thing, we know that this is equal to EB by construction. Okay, wait, oh my goodness, I forgot how I proved it. But I think we can try and utilize CG here, because by using CG, we can relate it to EB and somehow relate it to E prime B, what we have here. So this one and CG, maybe we might have. So we just need to prove that CG is equal to HB. Then our lemma is proven. Or we could prove that CI is equal to BF. That's also what we could do. But what should we try? Should we try like using CG first? Because I think that would be easier. How should we relate HB to CG? Okay. Okay. So this one. So we know that CE prime is equal to CI, obviously, and this is equal to AI minus, let's say this length is B, because here's B, and AI minus B, this is equal to, H minus B. Oh, no, that was, my R was too soon. H minus B. Wait, no, wait, this only works when this is a right triangle. I mean, isosceles triangle. Oh, sorry, you're looking at CE prime, right? CE prime, what is CE prime? CE prime is also equal to, yeah, CI, of course. CE prime is equal to BC minus BE prime. This is equal to BC minus HB. B. This is equal to CE prime BC minus okay, so we have what is CB? CB is equal to, this is quite tricky. So CE prime is equal to CI, equal to AI minus B, is equal to AH minus B. What is AH? AH is equal to AB plus BH, which is BE prime minus B. This is equal to C minus B plus BE prime. That's CE prime. Yeah. Okay, so we know that CE prime is equal to C minus B plus BE prime. CE prime minus BE prime minus CE prime. So we know that CE prime minus BE prime is equal to C minus B. What is C minus B? C minus B is actually, what is C minus B? This one minus that one, so this minus that. So BF or BD minus CD, which is equal to BD minus BE. So we have CE prime plus BE is equal to BD plus BE prime. So CE prime plus BE is equal to B. BD plus BE prime? Okay. We're almost done there. We're almost there. So what is BE? It's CD, right? So CE prime, like somewhere here, plus BE is equal to BD plus BE prime. It will perfectly match if E is equal to E prime from now on. But we need to prove that is if and only if condition. So we just proved that so if E is equal to E prime, then this is true. But we now need to prove that if this is true, then E is equal to E prime, so that we have if and only if condition. How should we go? Okay, let's utilize BC first. So CE prime is equal to BC minus BE prime. Minus BE prime plus BE is equal to, what is BD? BC, BC plus CD. Yes, nice. I think I proved it. Oh, what? Oh, yeah, it's minus. So BC minus CD. Yeah. Now what is BE? BE and CD, they're equal to each other. So 2 times BE is equal to 2 times. Nice. Therefore BE equals BE prime. And since E prime is on the line BC, yay! We proved this one too. So yeah, this lemma is true. Now the third one is actually, you could think of it like the corollary of it. So like, let there be triangle ABC where its incircle is tangent to BC at D. Draw if E is the point on the incircle such that DE is the diameter, then let if AE meets intersects BC at EF, then BF equals ABC, so EC. Let me just quickly check if that is correct. Let there be a triangle ABC where its incircle is tangent to BC at D. It's not E, it's D. Let E be the point on the incircle such that DE is the diameter. If AE intersects BC at F, then yeah. So simply just thinking, I'm just gonna copy and paste again. Not a big fan of drawing diagrams. So here we have Why can't I erase the highlights? Oh, nice. Nice. Okay. So this part right here is D. So this is D. And draw the diameter like this. And we have E right here. And this point right here is F. Then we have BF equals CD or DC. So it's actually quite simple to prove it from here. And that is, I just drew a line. Or again, it's going to be a visual proof. I don't want to write them. So we know that D is, so assuming that BC is horizontal to the x-axis, we can just like rotate our face to do that, or our perspective. We know that D is we can define D to be the lowest point and E to be the highest point. And again, because of our first lemma, we could actually magnify AE to get AF. And we just need to prove that F is the highest. Sorry. So we know that because E is the highest point on the circle, F must also be the highest point on the circle. But if we draw BC, if we extend BC, we know that F must be the highest point because F must be on the line BC because according to because X circles must touch BC, and F, which being the tangent point, is the highest point. So E is the highest point, and we also know that F must be the highest point, and we know that the highest point on X circle must be tangent to BC by construction. Cool. So we have F. So if we construct it like this, we know that the line AF exists. So what we just proved right now verbally is that the line AF exists. And now notice that because line AF exists, and by our second lemma, this is an if and only if condition, BF is equal to CD. So that completes our proof. Yeah, so actually when we just look at this is, I'm not sure, but I think this will be a really useful lemma, because let's just say that we have like a triangle, and that's like in center right here. If we draw it, then we know that these two are equal to each other. That's really nice. So yeah, thank you so much for watching this video. I think it was quite long, but I hope you enjoyed it. And tomorrow I'll come back with another very fun and interesting problem. Thank you, and see you tomorrow. Bye.